All right. Good evening, everyone. Thanks for joining us today for the very last session with the ICCI Cryosphere Pavilion here at COP29. So today we'll be talking about the Antarctic and Greenland ice sheets uh, when the ice is gone. So first we'll have Dr. Paul Bierman, who's a geoscientist with the University of Vermont. So first we'll have Dr. Paul Bierman, and geoscientist with the University of Vermont. So first, and following that, we'll also have Dr. Florence Culiani, who is with the Scientific Committee of Antarctic Research, who'll also be talking about Antarctica. And I'll leave it away to Paul.
Because when I'm projecting, I can't see anybody's faces from your group. So is everything good?
Everything's good. Everything's good. Okay. Yes.
So if something goes wrong, please just holler and we can work on it. Otherwise, I'm going to presume it's all okay. All right. Well, thank you all for having me. I realize it's late in your day there, and thank you for being there. It's obviously incredibly critical to our planet. I want to give you a brief survey today of what we know about Greenland's ice sheet in deep time, in the sense of hundreds of thousands of years of behavior, and when it was here and when it went away. And I'm going to start with this picture that you see. Those are pieces of plants recovered from under nearly a mile of ice at a place called Camp Century. Those are twigs and leaves and mosses. And I'm going to give you the conclusion of this talk, which is the ice sheet in Northwest Greenland disappeared 400,000 years ago and was replaced by Arctic tundra. And that is a fairly radical thing, because it implies at least 1.5 meters of sea level rise 400,000 years ago. The graphic I've shown up there is from Jörg Schaefer's paper. But not only am I going to talk about Camp Century, which is in the upper northwestern corner of Greenland, I'm going to talk about Summit and Gisp 2, where we have found very similar fossils, although the dating there is less certain. This is what the fossils look like from Gisp 2. This is a PNAS paper this summer that I led. Right in the center there is an Arctic poppy seed. And you're also seeing small bits of soil fungus, as well as spike moss fossils. All right, so let's go back to Camp Century. This is a United States military project built in 1959. In 1966, these two men were critical in recovering an almost mile-long ice core, the bottom of which they recovered 3.44 meters of frozen soil. And that is the frozen soil in the United States in probably 1966, 1967. That soil had a long history in various labs in the United States before it vanished in 1994 and then was refound by the Danes, frozen in Denmark, perfectly preserved. That's a picture of me in the red hat, looking at those samples in 2019. We have had a large National Science Foundation grant to understand those 3.44 meters of frozen sediment. These are 3 of the graduate students, Kat, Hallie, and Juliana, involved in that work. This is what the material looks like. A pretty average looking brown soil, except it's special. So in 2019, when we got the first test samples, we had about 250 grams of material to share between about a dozen laboratories. And so we saved every last bit of it. We washed it, we sieved it, and we filtered it to make sure we didn't lose anything. And watch the video carefully and look for the little brown things that are floating on top of that water that we're now filtering. And you'll see them go through that Buchner funnel under vacuum. Those little brown bits are the fossils. And if you couldn't see them in the video, I hope you can see them here. I'm going to have little green arrows that point to each of those individual bits of organic material. And remember, this sample came from under nearly a mile of ice. And this is what that entire sub-ice core looks like. On the left side of your screen, you'll see an early photograph of the core sometime before 1972. The labels on there represent the names of the samples. And on the right side, you'll see our reconstruction of that core taken from photographs in 2021. And you'll see that almost all the core is preserved. There are only a couple pieces that have been lost. And that's due to these two men, which we owe a huge thanks to. At the top is J.P. Stephenson from Copenhagen, and he runs their ice core repository. And at the bottom is Chester Langway, who ran the ice core repository in Buffalo. And between the two of them, they kept this core pristine for more than half a century. So what do we know? Thanks to Hallie Mastro, who I've put a photograph up here, we now know what the ecosystem looked like when the ice was gone in Greenland. And so there's poppy seed at the top, various other seeds. And what Hallie has done, this is her slide, is that she has mapped these fossils or subfossils to the plants that were there at the time. And this is, I don't know, it's kind of a spine-tingling thing for me to imagine as a botanist that she can go from these tiny little half-millimeter sized fossils to imagining a landscape. And she has worked down the entire core. This is the next segment lower. This one had some insect fossils. The chironomid pupa at the bottom is a form of a midge, which if you've ever been in the Arctic have certainly swarmed around your head. And these are what these various things would look like today if you were walking across the tundra. Not only do we know the ecosystem that was there, but thanks to work by Tammy Rittenhauer and her student Hawk, we know when the ice was gone. And these are 4 measurements. You can see them in red there, and then I've tried to put them, there's some updated dates on those that are very similar to them that are next to them in black. These are 4 samples from the top of the core, and they show us unambiguously that around 400,000 years ago, this area was free of ice and open to sunlight. The luminescence measurements measure the last time the sunlight landed on this part of Greenland. And that is a paper in Science that we had last summer. And modeling by Ben Kiesling, which is shown in the lower right panel, mandates that if the ice is gone at Camp Century, there's at least 1.5 meters of sea level rise coming from Greenland.
Thank you.
And can you see, you can see this now. Great, fantastic. Okay, so in 1993, the US drilled a core at GISP-2, and this is some VHS video, thanks to Mark Twickler, of that drilling at GISP-2. And you can see that people are well equipped to use the fairly toxic drilling fluid that they were using there. And at the bottom of GISP-2, they brought up more material, mostly rock that you'll see here, but they also brought up a little bit of sediment. And that yellow shows you where the sediment was. We call that glacial till. And this is a photograph of that 8 centimeters of glacial till. And we have another photograph of it from the other side that shows you it's a mixture of sand and gravel and silt and small clasts. And that glacial till was studied just once and then put away in a plastic bag for the last 30 years. We got a hold of that glacial till, and Hallie did the same thing on that. And this is last summer's paper. And remember, this is the center of the Greenland ice sheet. She found willow fossils, she found spike moss fossils, and she found poppy fossils. And together, that indicates that the center of Greenland was deglaciated. The only age we have on that now is work by Jorg Schaefer that suggests it's within the last 1,000,000 years. We can't do any better than that. And the landscape probably looked like the one you see in my slide here, where the helicopter is sitting. It was rocky, very little vegetation, probably dry. So why does all this matter? This matters because when Greenland was deglaciated 400,000 years ago, and likely when it was deglaciated 1,000,000 years ago, looking at the carbon dioxide levels, carbon dioxide in the atmosphere was no more than 300 parts per million. That's about the level in the 1940s. And today, of course, we're at 420 parts per million. So we can look at when this core was, when the sediment in this core that we analyzed was deposited, and it's right there at a carbon dioxide level of 280 parts per million. Yet we had a community, an ecological community that was tundra there, and the ice was gone. So nature at far lower carbon dioxide levels has removed at least part, and at some time, all of the Greenland ice sheet. So what does this mean? Greenland was at least 90% ice-free within the last 1.1 million years at CO2 levels far less than they are today. And so I'm going to take Wally Broker's sort of very famous statement that climate's an angry beast and we're poking at it with sticks, but I'm going to change that a little bit. And I'm going to take climate out and say Greenland is an angry beast and we're poking at it with sticks. And from this, I take away that Greenland's ice sheet is naturally fragile. We have dramatically increased the thermal forcing, the radiative forcing now on our planet and are warming this planet. And we are destined to once again lose that ice sheet. So I want to take a last sort of short diversion here in a couple moments. And I want to talk to you a little bit about the history. I've shown you the science, and I want to talk a little bit about the history behind this. I just published a book this summer with W.W. Norton that's the result of the last 3 years of research looking at how we know what we know about the Greenland ice sheet. The New York Times did a Q&A on this that you might find interesting. The New Yorker just did a really short review on the book. But the idea here is to bring our findings, the scientific findings I just showed you, to the much broader community in an attempt to influence policy and to get people to realize how important Greenland is. So the first major modern expedition was Wegener's. He's up in the upper corner in native Greenlandic gear. And he placed men on top of the ice sheet during the winter of 1930-31. And they, for the first time, understood the layering or the stratigraphy of ice as a way to understand the climate. The US then got very interested in Greenland in World War II. In fact, there were Nazi bases. There's a photograph of a captured Nazi flag in Greenland. But really, it was the Cold War. And it was the threat of the Soviet Union that amplified US study of cold regions and snow and ice. And you can see a soldier there digging a snow pit. This was the first collection of ice cores. And that led to people living on the ice cap. So in 1953, the Army built two bases. They called them weather stations, but they were in fact radar stations underneath the ice. And they were long metal tubes like this. And they were featured in magazines, but they were top secret. The military wouldn't say where they were, but they said what they were. This is a magazine for men from that time. And this is what the bases look like. So men lived for months at a time inside the ice sheet. And all of this was motivated by a fellow named Henri Bader. And Henri Bader was a Swiss man. He became a US citizen. And he developed the technology that we use today to study ice sheets and to operate on ice sheets. Vehicles like this, he was integral in the engineering and development of, but particularly he had a vision about ice cores telling us about climate. And this is the first US ice core in Greenland being taken at a place called Site 2. They got down about 1,300 feet. And just for fun, and this a bit of Bader's voice talking about why it's important to do ice cores. He's long dead. He died in the 1990s, but there was a recording of him made on a Voice of America broadcast that we'll listen to. Hopefully, you'll be able to hear it.
The purpose of deep ice coring is to get information on conditions deep down in the glacier. And since conditions are simplest on the high ice caps, this is where we have been drilling.
So Bader's work reached its pinnacle at a place called Camp Century. And this was the US base 138 miles into the ice from the margin, featured in the front of Popular Science in February 1960. So absolutely no secret. We wanted to make sure that all of our enemies, particularly the Soviet Union at the time, knew that we had a military base on the ice sheet. It was constructed with large plows imported from Switzerland that dug deep trenches. It's a short video of those plows. They did a lot of filming up there, so we have excellent film records of what went on. Then they put heated barracks inside the tunnels like this, prefab barracks, 72 degrees, where the men lived and ate and smoked and slept. They had a full dining hall, a mess hall there, where they had as much frozen meat as they wanted, huge frozen lockers of meat underneath the ice, steaks and chickens and turkeys, and they had a drill rig. And for 6 years they drilled, and they perfected deep ice core drilling. It had never been done before. And the American military pulled it off and brought back almost a mile of ice core. This whole thing was heated and had its electricity from a portable nuclear power plant, the first of its kind and the only one of its kind ever to operate in an ice sheet. Just to give you a view of what it might have been like in the camp, this is some very early photos. There's no frost on the walls. These are GIs walking down what they called Main Street, 1,000-foot long tunnel, which had branches coming off the side. Because of the nuclear reactor, the Army bragged that there were unlimited hot showers for the men and unlimited power to brush your teeth, or as you'll see in the next bit of this, to shave your face with an electric razor, all of this inside the Greenland ice sheet. So just a sort of a miracle at the time of technology. And the reason I say this is that most people would have thought this was absolutely impossible at the time. Yet a dedicated group of people in less than a decade went from knowing very little about the ice sheet to knowing enough to engineer a solution to put people inside the ice. And that is my ray of hope for our future that I'll come back to. This all finished with a fantastical demonstration at the Pentagon, where these three men, Chet Langway is in the middle. He's the geologist really in charge of this, and on the side is one of the lead drillers. But they walked into the Pentagon with pieces of the ice core, and they served it in Coca-Cola. And the bubbles in the ice core, that this piece was about 2,000 years old from the time of Christ, the bubbles popped as the military brass listened to that ice. And the New York Times reported that the Coke tasted like Coke and the ice tasted like ice. And that was kind of the end of the big fanfare on that core, although, of course, paleoclimate has been amazingly well served by this. To put this in the context of today, in 1962, Life published this advertisement from Enco, Humble Oil Company, ended up being Esso, ended up being Exxon. But I think it's really interesting for us to reflect on this. And it's one of the reasons that I wrote the book, is to try to put the loss of glacial ice and our appreciation for glacial ice in context. This advertisement claims that each day Humble supplies enough energy to melt 7 million tons of glacier with an exclamation point. They are proud of their ability to melt ice with energy. This giant glacier has remained unmelted for centuries, yet the petroleum energy Humble supplies, if converted to heat, could melt it at a rate of 80 tons each second, another exclamation point. Think about how we have changed our global context from then to now in these last 60 years, right? It's no longer popular to melt ice. And that again gives me hope that there is the ability to change. Just for fun to wrap this up, the futurists of the time actually imagine that we might all be living in cities under ice. This is a cartoon that was syndicated around the country in the early 1960s. This is February 1960. And this is based on Camp Century, right? Except they're cars, futuristic cars and freight lines and things like that, all operating underneath the ice. So why does this matter? This matters because Greenland is controlling, in large part, for the moment, our global sea level rise, along with thermal expansion of seawater. Of course, Antarctica, as we'll hear in the next talk, is also very important. But we're already starting to see the effects of melting ice. That's a photo from my hometown. That's Baltimore, Maryland, and a king tide. And the area that I worked as a high school student down by the water now flooded. And I have no memory 40 years ago of that flooding, but it obviously floods today. And then a map out of Nature Climate Change of the populations at risk from flooding by the year 2100. So what I try to do in the book, and I'll flip over to a photograph of that, is to take the case public and to try to confuse the narrative a bit, where at least in the United States, we think about red states and blue states and conservative and liberal. And in many ways, our climate, our thinking on climate is broken across those lines. But when you read that the US military has been so involved in what we know about climate science and our ability to work and understand Greenland, it blurs all those lines. And that's my goal. My goal in writing this book was to blur those lines, was to bring the public in a way that's understandable of how glaciers work, how ice sheets work, why it matters, and to see if we can get beyond this political divide on climate. And the last thing I'll say is, as I mentioned, these men who managed to develop a nuclear reactor, plans for an Arctic base, drill the first ice core. They did all these things that people at the time thought would be impossible, but they did it. And that's I guess if I have a happy ending to the book, my thinking is humans are ingenious. We are creative and we solve problems. And when I finish teaching my climate class next week here, I've got a couple hundred students in a climate change class. What I say to all of them is, here's my example from the past of solving a wicked complex problem. And all of you, this upcoming generation of really smart, innovative students, need to put your energy to solving the climate crisis right now, and take hope and take an example from these people in the 1950s who obviously solved a smaller problem, but they did that. And then in the next decade, we went to the moon. So solving these problems is possible. So I'll leave it there. There's some websites you might find useful. Our research website is campcentury.org. My personal website is up there, our laboratory website. And then there's the Norton, W.W. Norton, where you can find the book if you're interested in reading it. Thank you for having me today.
So yeah, I mean, because I wanted to try to follow a bit Paul's track, but it will be fairly different for sure. Anyway, I wanted to start about talking about when Antarctica was ice-free, like a little bit to mirror Greenland, but actually it's fairly the same story. So it was, we are sure it was totally ice-free during the Cretaceous, actually. So Cretaceous is before, 60 million years ago, broadly. I mean, the 65, actually, that's the Cretaceous tertiary boundary when the dinosaurs died, actually. And at that time, CO2 concentration was very elevated. It was above 1,500 ppm in the atmosphere. And so global mean temperature was about 25 degrees, so it's about 10 to 15 degrees higher than today. And at that time, Antarctica was completely deglaciated. It was not completely at the South Pole, though, because of plate tectonics, it migrated slowly and reached basically its position a little bit before the Eocene. So the representation that you see is artist view that has been performed by Avi, I think, author, when they discovered some roots in a sediment core records of Antarctica, but very close to the margin in Pan Island Bay. Pan Island Bay is, if you can see the map on the top of the slide, there is a red dot. Okay, this is one of the most sensitive points of Antarctica right now, most sensitive part of Antarctica to ocean warming. And they discovered from sediment cores from the continental margin some roots, actually. So that's a scan from X-ray for magnetic analysis of this sediment core. And those are roots, actually. And when they discovered them, it was definitely the proof that this part of Antarctica was definitely covered by forest, actually. And because of the temperature and greenhouse gas, it was not very difficult to prove with ice sheet modeling that it was totally ice-free at that time, actually. Then we got some other geological archives that showed us that Antarctica started to glaciate basically when I represented this vertical blue bar, broadly 34 million years ago. So this graphics here shows you the evolution of reconstructed temperature over the past 70 million years. Okay, so from left to the right. And it shows you that before this blue vertical bar, so roughly 34 million years ago, temperature was much, much higher. Okay, and then after this shift, okay, there was a kind of stabilization in temperature before it drops again until we meet modern climate, global mean temperature about 10 degrees, okay? This blue bar then mark the growth and the birth of the Antarctic ice sheet, of course not as expanded as it is today. And later on, when the temperature drops further, we develop also periodically, broadly every 100,000 years, some other ice sheets over North America and over Eurasia, okay? So, what was the CO2 concentration during those temperature fluctuations? So we start with, I say, about 1,500 ppm of CO2 in the atmosphere. Then, as far as we go through the Eocene period, so before the blue bar, we have 1,000 roughly ppm of CO2 in the atmosphere. And then we have this transition we call Eocene-Oligocene transition. This is when Antarctica starts to glaciate, basically. And we drop to about 800 ppm in the atmosphere. And then slowly we go down to 400 ppm through the Miocene. And when we cross the Miocene-Pliocene, we stabilize a bit, 400 ppm. That's why we take the Pliocene as an analog for our future, our present day situation, and a little bit our future under Paris Agreement scenarios. And then we drop below 300 ppm, as Paul said before, okay, for the last 3 million years of the Earth's history. Then I wanted to show you how the Antarctic ice sheet expanded during that time, and then I will show you how it retreated also. But first, I wanted to show you how it expanded, because glacial cycles are not only, let's say, a recent aspect of the Earth's climate history, but it's also something that existed before with different pace, different amplitude, but orbital settings have always been fluctuating and modulating the glaciations, actually. So zooming over the last 40 million years, okay, we can see after the transition when Antarctic started to grow, okay, the first glaciation, they were already fully expanded, okay, and geological evidence and sediment cores really show us, because we found what we call ice-rafted debris, so small pebbles that have been eroded from the bedrock below the ice sheet and transported away in the ocean, drifted away when the icebergs discharge from the ice sheet fronts when it reaches the ocean. And so it was quite expanded at that time already. And then when CO2 dropped about below 500 ppm, also all West Antarctica become completely glaciated. And then during our, let's say, much modern setting of the climate, the Antarctic ice sheet expands even further on the continental margin around Antarctica. So glaciations have always been very extensive in Antarctica. What about warm periods? So warm periods are more of interest for us now if we want to understand the amplitude of possible sea level range in the future. But at the beginning, the Antarctic ice sheet was able to retreat, not that much actually. I mean, this is what models say to us, despite the high CO2 concentration, which means that Antarctica, contrary to Greenland, is stable even with higher CO2 concentration, okay? Then we move in time and we arrive to the Miocene with peaks interglacials or warm periods around 500 ppm sometimes. And you see that the sectors of Antarctica that deglaciate are fairly the same. And we arrive to modern configuration where you can see that some sectors retreat a little bit further compared to what happened in the past warm periods in Antarctica. And this is because, you know, an ice sheet, when it advances and retreats, it just erodes the bed beneath, okay? And because of doing that, the bed is just deepening. And so it means that the foot of the Antarctic ice sheet is just becoming slowly more vulnerable to oceanic warming because it's going below sea level, okay? But this erosion has been very gradual in time. So at the beginning, it was not very sensitive to oceanic warming because most of the basins that are now sensitive to oceanic warming was still above sea level. And by advances and retreats of the ice sheets, it has been those basins have become slowly below sea level, okay? And so our marine-based sectors today are sensitive because of the modern settings of accumulation of advances and retreat and erosion by the Antarctic ice sheet itself, actually, through time. So on the modern yep, okay. No, let's just keep it going, okay. Pretend not hearing anything. So on the modern settings, I put it two plots actually, because the simulation I am showing to you have been done with a concentration prescribed at 500 ppm of CO2 in the atmosphere. The bottommost Antarctic simulations have been run with 840 ppm in the atmosphere. Okay, so it's something that would correspond to the worst case scenario at the end of the 21st century. So you can see that the retreat is even more extensive at that moment. Okay, cool. What the sea level reconstruction says, okay, for those periods. So started 23 million years ago. Yeah. Sorry, I have to go back. Yes, better. So we have. Yeah, I mean, there is nothing that we can do. I don't know if there is someone passing by and trying to hack our system, but well, anyway, past sea level reconstruction. So past sea level reconstruction actually, they show that. Okay, well, I proceed. So for past sea level reconstruction, sorry for this interruption, but it seems that already we have some interferences with someone else. Yeah, but I'm speaking for the people online, not for you. Okay, so for paleo sea level reconstructions, so we have during the Miocene period, so it was 23 million years ago, okay, global mean temperature. Yeah, it's complicated now. Okay. Okay, so we have temperature, global warming about +5 to 9 degrees, and a CO2 concentration about 500 ppm, and we have a sea level rise of about let's say 20 to 25 meters above present day. Okay, means that large part of Antarctica was melted at that time because it was the only ice sheet that existed on Earth. Okay. Then we have the Pliocene period, I say 3 million years ago, and this is just before the CO2 concentration drops below 300 ppm. So at that time, concentration was already, well, but it was still 400 ppm, and global warming was about plus 2 degrees, basically 3 degrees. And we have both Antarctica and Greenland ice sheets that contributed to sea level rise. And the reconstruction show a range about 15 meters, okay? Then after the drop of CO2 of 300 ppm, below 300 ppm, basically, we ended up with global warming of plus 5 degrees, plus 0.5 degrees to plus 1.5 degrees, which is very similar to our Paris Agreement, basically. But we have still a sea level range reconstructed about 15 meters, okay, with both Antarctica and Greenland contributed together. And then the most recent big interglacial that we have, it's about 128,000 years ago, and it's a CO2 that is definitely below 300 ppm, okay, and a global mean warming about 0.5 to plus 1.5 degrees, okay, so still in agreement with Paris Agreement. And we have a range of sea level reconstruction around 5 meters with both Antarctica and Greenland ice sheet contributing. So from yesterday to tomorrow, yeah, I wanted to show you that because all the dots that you see around Antarctica, actually, they're the sediment core records that we do have nowadays. Well, we have a lot of also very short ones, okay, that only records like 10,000 years of climate history. The one I'm showing to you are the one that allows us to go back million years back in past, okay? So the deep drilling around Antarctica, and you can see that there are not a lot of dots actually, and they're all concentrated in areas where we can easily reach bases, or because it was really of interest, or simply because it was not in the pathway of icebergs drifting, for example. On this map, okay, that shows you the bedrock of Antarctica without the ice sheets, you can see the extent in magenta. That's what we think was the extent of the Antarctic ice sheet 3 million years ago, okay, so before CO2 concentration dropped below 300 ppm. And then after when it dropped in below 300 ppm, the extent is shown in blue. So you can see that, of course, though we think Antarctica retreated during the most recent interglacial, we don't really know exactly to which extent. It's still a matter of debate, but we know that it retreated in some sectors, that's for sure. So we still don't know how much, and everywhere, we are not sure that everywhere retreated. Now, next to this plot, I show you the changes in elevation, okay, that our satellites have been recorded over the past decades, okay, and you can see that some of the areas where you have some ice loss, actually, also corresponds to areas that in the past retreated, okay? So this is very, I mean, the coincidence is very nice, okay? So it means that even though we are using models nowadays to reconstruct the past extent, I mean, it's really matching what we are seeing today as sensitive areas in response to climate change or both atmospheric and oceanic warming. So now going back to this plot, because I really like it very, very much. If we go back to the mid-Pliocene period, okay, this corresponds to our current indices plus 2.5 degrees, plus 3 degrees by the end of the 21st century, okay? And then we have those two interglacials that correspond to our Paris Agreement lower boundary, okay, most conservative boundary. And then if I plot our projections of sea level rise in the future, you can definitely see that even in case of plus 4 degrees of warming, would still stay in the range of the Paleo-data reconstructions. Okay, so I really wanted to show you that because I think that both what we have been told by the ice core records and the sediment records, together with the modeling efforts both in Greenland and Antarctica, plots toward a very nice picture of validation for our projections and the sectors that are very sensitive nowadays to ocean warming and atmospheric warming compared to what those past archives told us, okay? So for both Greenland and Antarctica, yeah, there have been some times where they have been ice-free. Antarctica is definitely much more sensitive than Greenland is much more sensitive than Antarctica because it's not located really at the North Pole, but also much south compared to North Pole. Antarctica, it's much bigger, so of course to melt the entire Antarctica it takes some time, okay? But it has been ice-free, and probably the huge part of West Antarctica has been ice-free several times in the past. And there are very recent expeditions that are still, from which the sediment core is still being analyzing. And we got very nice continuous records of those past glacial cycles. So we will soon have some confirmation about probably the magnitudes of the retreat in West Antarctica. And I wanted to conclude on these slides, going back to vegetation, actually, because what we are seeing now is the greening of Antarctica, okay? This is in the peninsula, so it's not in sub-islands, subantarctic island, it's on Antarctica. And we have seen an increasing greening areas over this sector of Antarctica. I mean, this graph shows you the increasing the greening areas over time. Okay, so it has been increasing over the past decade, very fast, and we are now at a concentration of 427 ppm, and a global warming that is plus 1.3 degrees above pre-industrial level, and we are already substituting the ice by vegetation. So not only this happened to Greenland in the past, and this is already also happening in Greenland, the greening of the land around the glaciers, it's also happening to Antarctica. So this is effectively testifying that there are huge ecological changes happening in Antarctica now. Vegetation is a fantastic proxy for the evolution of climate, because plants only grow if they have temperature and water supply. So that's it. So I think this sets the scenes for what we have been saying here, that we need to preserve our cryosphere by maintaining our Paris Agreement limit of plus 1.5 degrees. Otherwise, a huge bunch of different aspects of the climate system will be just passing through a tipping point with no reversible changes possible. Thank you very much.
You want to moderate questions to Paul?
Oh, yeah, right. Are there any questions from the audience here or online for Paul?
Yeah, I think you should.
Yeah.
Hi, Paul. Really interesting talk. I just had a quick question about, some of the military history that you were talking about there. Given that you've done all this research and written the book as well, and it's probably too early to say at this point, but has it led to any kind of dialogue that you were hoping it would sort of veer towards any kind of discussions with, different parties of any kind? Like, I would love to know, how it's been.
Yeah, I would say not at the level of the government yet. Certainly with people associated with our university, with people in New England where I've given talks. We have an institute that started for ecological economics, but now has spread to the environment as a whole. And I've been engaged with the board members on there, which represent a cross section of people around the country. But no, the book's only been out now for about 2.5 months. But I would love to find a way to get into more policy-rich circles with this to talk about it. I mean, that was certainly my goal. So if there's any ideas you all have on how to help do that, I would be all ears for something like that.
Yeah. Hi, Paul. This is sort of a question for both of you, maybe in a way, because part of the difficulty that we deal with here is we're talking about such long timescales. And yet, what I take away from both of your presentations is that given where we are with both CO2 and temperature right now, we're way above where we would expect both ice sheets to be basically partially or even completely deglaciated. And yet, the comprehension of that just seems to be really lacking here. Or, again, because it's a long time frame, maybe it makes it very, very difficult for people to worry about that. We're being constantly pressed, I would say, as an organization to talk about the next 5 years, talk about the next 10 years. And yet when it comes to this, we can't because it's not going to happen in the next 5 or 10 years, even if, in a sense, we may already have triggered it, right? We're way above on CO2. We're heading way upwards on temperature. I'm just wondering if the two of you could think about that and comment on it. This pressure to talk about only the near term, and yet both of your talks are really about enormous time frames, but also that we're de facto in those areas where we have just massive levels of sea level rise that aren't even contemplated right now. People look out towards 2100, they're talking about 20 centimeters, 30 centimeters, 50 centimeters. You're talking about 50 meters in one of these areas. So have at it. Any thoughts or suggestions?
Or do you want to go first, or do you want me to make a brief comment? Because it will be brief somehow.
Oh, go ahead. You can comment first. I'll keep thinking.
Okay. Okay, fair enough. So to accumulate ice, you need a lot of time. Anyway, to melt it, you also need a lot of time. So the more ice you have to melt, the more time it takes. That's for sure. Okay. So that's why you also have long time scales. Okay. Melting a glacier is much faster. We are definitely above the Greenland threshold, that's for sure. And we are definitely above the West Antarctic threshold, that's for sure, because West Antarctica started to be completely glaciated when we were around 400 ppm. So we reached definitely the CO2 level when Paleoclimate Archive showed us that Antarctica got glaciated, okay? We know anyway that the ice sheets, they have they're resilient somehow because, of course, the pathway to glaciates in terms of temperature and CO2 is different from the pathway to deglaciates. So it means that you can glaciate an area more easily. It's more difficult to glaciate an area than to an ice sheet to an area. Than to melt it away completely. And this is what we call the hysteresis cycle of the ice, actually. Now, the range of this hysteresis cycle for Antarctica is large. That's true. However, it will not resist the worst-case scenario that we talk always about, the 8.5. This is the upper bound of the hysteresis for Antarctica anyway. So our projections, I think they really well represent what the physics of this hysteresis in terms of ice volume, sensitivity to temperature and CO2 would show for Antarctica. For Greenland, it's much more sensitive than Antarctica. So we are definitely well above what I can see from my archive. Forward to you.
Yeah, so I'll take a different approach to that. And I think it's rooted in my teaching and what I see works with students. We can talk about exactly hysteresis, and I teach that in class. But I think to reach the public and to reach policymakers, we need simpler explanations. And so the two paths that I typically go down, the first one is thinking about your freezer at home. And if you leave your freezer door open, the longer you leave the door open, the more food you're going to melt. And I think that's a very direct analogy. So the longer we leave large amounts of CO2 in the atmosphere and the longer we leave the climate warmer, simply the more ice we're going to melt. And I think you can temper that also with arguments about cost and arguments about impact. And you certainly can go to the hysteresis argument where at some point you put the Greenland ice sheet in a tailspin and it's not going to recover from. Where as the ice starts to lower and is in a warmer atmosphere, the melt speeds up. But I think that's all on the order of decades at the best and centuries at the longest. And that's not how our political system is working right now. So I find the most effective communication to be things on that shorter time scale. The analogy to your freezer, but then also, the data on the melt at Greenland's surface. And so you can look at the last 30 years of melt history as imaged by satellites and see years like 2012 and 2019 and show pictures of rain falling at summit. And I really think we have to work at a time scale that matches the time scale of the political system, which is years and human lifetimes. And I found that really effective when I give talks to say, hey, if you look back on the record, melt happens at summit once every couple centuries in the ice core record. But it's happened half a dozen times, in the last 100 years, and there's something different about that. It's, as someone who teaches climate and glaciers all the time, it's just really hard to deal with these multi-century timescales. So I think we have to find a different way of communicating the fragility of ice sheets like this. And maybe it's, the videos of thundering amounts of water pouring off the ice and into the ocean in the Watson River. But it's not our models, and it's not our million-year predictions. That the most successful thing to me in giving talks has always been the pictures of the fossils and the plants that I showed you from Halley, and showing that literally a mile of ice vanished at Camp Century and 2 miles of ice vanished at GISP 2, and convincing people that these ice sheets are fragile, especially the Greenland's ice sheet. I don't know if that's a satisfying answer, but it has worked well with numerous different audiences for me to convince them that, in fact, these ice sheets are vulnerable, even if it's going to take a couple generations to show that.
Okay, thanks, Paul. Yeah. Okay. Paul, thank you very much for joining us here at the last event, the very last event of the Cryosphere Pavilion. Being disturbed by Azerbaijan music, weird YouTube sound also during my presentation. So anyway, I think it has been entertaining. I think now we will just close the door and meet again next COP.
Yeah, thank you so much, Paul. It's really nice to see you in this last side event at this COP and closing down the Cryosphere Pavilion. We also, by the way, had, what is he called, Cop Claus, who came in and listened to a part of the presentation. Guy dressed as Santa Claus has been wandering around for 2 weeks. Thank you, everyone who's worked at the Cryosphere Pavilion. Why don't you all come up here, say hi to Paul, say goodbye to any people viewing on the live stream, especially the ECSs.
All right. Well, thank you all for being there. Much appreciated.
Okay. Thank you. See you maybe in Brazil.
See you.
Bye. James.